Alright, so I left off at number 47 we just did, so here's 48. What is meant by STP? So STP is standard temperature and pressure. So standard pressure is 1 atm or 760 millimeters mercury or 760 torr. Standard temperature is 0 degrees Celsius or 273.15 Kelvin. Number 49, combined gas law is P1 V1 over T1 equals P2 V2 over T2. Number 50, ideal gas law, PV equals nRT. 51, R equals 0.0821 liters atmospheres over moles Kelvin. Alright, well, let's do this one right here. 52. Again, at STP, 1 mole of any gas is 22.4 liters. 53. So this looks like a gas law problem. 25 milliliters of gas is trapped in a syringe at 27 degrees Celsius. What would happen to the volume if the temperature is increased to 427 degrees Celsius? Assume pressure is held constant. So for this, we're going to be using the combined gas law. P1 V1 over T1 equals P2 V2 over T2. And it says pressure is held constant, so we're going to go ahead and erase pressure out of this because it doesn't change. Okay. And let's see, what am I looking for? What would happen to the volume? So I'm looking for V2. Well, I'm going to get V2 by itself by multiplying both sides by T2. T2 cancels out. This is my formula. So my T2 is 427 degrees Celsius. For this formula, you have to convert Celsius into Kelvin. So adding 273 to that is going to give me 500. So 500 point Kelvin times V1, which is 25 milliliters, divided by my T1, which is 27 degrees Celsius, or, did I do the math right here? I did the math wrong here, didn't I? 427 plus 273 should give me 700. 700. And then 27 degrees Celsius is going to give me 300 point Kelvin. There we go. Do the math. 700 over 300 times 25 gives me, with two sig figs, 58 milliliters. And you might think, wait, it went from 27 to 427, so shouldn't it go up by like 15 times? Well, not really, because in Celsius it didn't really, the temperature didn't go up by 15 times. It only went from 300 to 700, so it went up by, what is that, 233%, something like that. Alright, 54. Imagine 35 milliliters of gas is contained in a container like the one above. Pressure is 720 torr. At constant temperature, what must the pressure become to reduce the volume down to 16? Okay, so let's see. Assuming constant temperature, so it's going to be P1 V1, not T1 is canceled, equals P2 V2. We are solving for what must the pressure become, so that's going to be P2. P2 equals P1 V1 over, just make sure I'm good on this, P2, so I'm going to get V2 by itself over here. There we go. Okay, let's plug in our values. P1 is 720 torr. Now remember, you don't have to convert this to atmospheres. That's the ideal gas law. This just means whatever I get out is going to be in torr. Times V1, which is 35 milliliters, divided by 16 milliliters, which is my V2. What must the pressure become come to reduce the volume down to 16? For some reason I feel like I didn't do this correctly. V2, get that over here. What does pressure become? The wording of the question is a little odd, because really pressure, like, we don't really influence pressure directly, like we influence volume or temperature. So really what it should be saying is, like, I should have said if you adjust the volume, what would happen to the pressure? But either way, we can still solve this in this way. So it's 720 times 35 over 16. And with 2 sig figs, my answer comes out to 1600 torr. So you adjust the pressure to 1600 torr, the volume would shrink. Alright, 55. Calculate the density of pure HCl gas at STP in grams per milliliter. Alright, this is a good question. So, Cl2 gas is going to be 2 chlorines. So let's look at our periodic table. Chlorine gas has a mass of 35.45 grams per mole times 2. So for Cl2, it equals 70.9 grams per mole. So if I have 1 mole of this, it's going to equal 70.9 grams. Okay? If I have 1 mole of this gas at STP, I know what the volume is going to be, which is 22.4 liters. Okay? So I'm looking for grams per milliliter. Well, if I wanted grams per liter, it would just be grams over liter. So let's convert this to milliliters by saying 1,000 milliliters per liter. Liter cancels liter. So this is going to be 22,400 milliliters. So basically, if for 1 mole of the gas, my volume is 22,400, my mass is 70.9. Let's do the math. 70.9 divided by 22,400, it's going to be a tiny number, equals 0.00317 grams per milliliter. Okay, number 56. Calculate the volume of 3 moles of methane gas at STP. Well, this one's easy. If it's at STP, I know that each mole is 22.4 liters times 3 equals, what's that going to be, 67.2. Easy. 57. How many grams of N2 gas are present in 50 point liters of N2 at 1.35 atm and 28 degrees Celsius? Well, this is just going to be a ideal gas law problem. Now, you can't solve for grams in that, but I could solve for moles and then convert that to grams. So, PV equals nRT. I'm solving for N, which is moles. N equals PV over RT. Plug in what we know. 1.35 atm. That's good because my pressure has to be in atm. Volume is 50 point liters. Again, it's good because it has to be in liters. Divided by R, which is 0.0821 liters atmospheres over moles Kelvin. Also divided by T, which is 28 degrees Celsius. Now you have to convert that to Kelvin, yes, to put that in. So that's going to be 301 Kelvin. Check our units. Atmosphere, atmosphere, liter, liter, Kelvin, Kelvin. We're left with mole as that like double denominator, which means it comes up to the top. So N equals 1.35 times 50 divided by 0.0821 divided by 301 gives me 2.73 moles of N2. But we're looking for grams, so N2 is going to be 28.02 grams per mole of N2. Carefully, you don't just do N here. With 2 sig figs, because I see 2 sig figs, I get 77 grams. All right, 58. What is meant by the terms heat of fusion and heat of vaporization? Well, heat of fusion is the amount of heat it takes for fusion, which is melting, to occur. So it's the joules that it takes for 1 gram of a substance to melt. Heat of vaporization is the same thing, but with boiling. So it's the amount of heat in joules that it takes for 1 gram of a substance to boil. 59. Solute and solvent. Basically, a solute dissolves in a solvent. So, classic example is water is the universal solvent, and when you have like salt water, the salt is the solute. Let's see. Number 60. Formula for molarity. Moles per liter. Number 61. How does temperature affect the solubility of solids in water? Well, for this, basically, hey, I'm filming something. You can come in and clean, though.
I'm taking a note. I just saw lights on.
Oh, all right.
Have a good night.
You too. All right, so solubility affect the solids in water. Basically, as you heat something up, the solubility will increase. That's for solids. Verse 62. How does temperature affect solubility of gases in water? Well, it's sort of the opposite. The colder the water, the more gas you can dissolve in there. Actually, the reason for that is, let's say this is our water here. Okay, and inside, let's say we have some gas dissolved, like we'll call this CO2 gas. Okay, now gas is floating around and it's trying to go up, and it's trying to go down, and basically this can remain dissolved in the water as long as it doesn't break through from the surface. Well, up here at the top, the colder the water is, the stronger the bonds at the top, and not only that, the stronger the bonds throughout. So this can be really held in place by strong bonds throughout the water. Well, if the water heats up, all of a sudden these bonds kind of loosen, and all of a sudden the gas is more able to escape. All right, 63. What is a saturated solution? That's a solution in which you can't dissolve any more solute in the solvent. It's completely full. So, if you took like salt water and mixed like way too much salt into it and tried stirring it around, and you notice a bunch of it just sits at the bottom, that's saturated. And one way you could actually get that to dissolve is by heating the thing up and then stirring it again. 64. We're getting there. How many grams of solid potassium sulfate are needed to make 200 milliliters of a 3.00 molar stock solution? So this is a stock solution problem. My formula is molarity equals moles per liter. I am looking for grams, but grams is in here, so I'm going to use moles and then find grams. So let's plug in what we need to know. It's a 3 molar solution, and that equals moles over how many liters? 200 milliliters, so that's 0.200 liters. Multiply these together, it's 0.600 moles. Okay, and that is moles of potassium sulfate. So let's find potassium sulfate, which is going to have 2 potassiums, so 39.0983 times 2 plus 1 sulfur, 32.066, plus 4 oxygens, because it's K2SO4, so 4 times 16. 174.26 grams over mole. And the answer I get with, let's check sig figs, 3 sig figs is 105 grams. Okay, let me check, that seems kind of high. Let's see if it matches my answer from the answer key. Yep, yes it does. All right, 65. If 200 milliliters of a 6 milliliter solution of potassium iodide is mixed with 500 milliliters of a 2 molar solution, what's the molarity of the resulting solution? I like this one. So let's see, for molarity, it's moles over liter. So we need to find how many total moles went into the thing, how many total liters went into the thing. Well, liters is easy. It's 200 milliliters of the first, 500 milliliters of the second, so it's going to equal 0.700 liters, because you take 200 mils and 500 mils and mix them together. A little bit harder is going to be the, actually it shouldn't be that bad, the moles. Well, we need to find how many moles were present in that first one. So in the first example, it was 6.00 molar, and it was 0.200 molarity, liters. So 6 times 0.2, that's going to give me 1.2, 1.20 moles. So that's how many moles were in that first beaker. The second beaker had a molarity of 2.00. And we used 500 milliliters. I'm going to say 0.500 down here. So this is going to equal 1.00 moles. So basically, if you had the two beakers, the first one had this much, second one had this much, add them together, 2.20. Work it out. See what we get. 2.20 moles divided by 0.700 equals 3.14. The unit is technically moles per liter, but you could also just put molar like that. 66. Hydronium ion, H3O+. This is crucial for acids. Basically, it's a water molecule with an extra proton stuck onto it. 67. Suppose that 45 milliliters of 0.750 molar hydroiodic acid. Oh, okay, titration problem. So let's see. Basically, what we do is we look for the moles of the one that we know, or that we're able to figure out. So I have 0.750 molar hydroiodic acid, HI aqueous. Okay, that's the molarity, and I have 45 milliliters of it. So that's 0.045 liters. And I'm looking for moles, so we're going to multiply 0.045 times 0.750, which gives me 0.0338 moles of hydroiodic acid. Okay, so I now found moles, and let's see what we need to do here. So this is mixing with sodium hydroxide. So I need to know what's the mole ratio between hydroiodic acid and sodium hydroxide. Well, my equation is going to be hydroiodic acid plus sodium hydroxide is going to create, H goes with OH to form liquid water, I goes with Na to form NaI, that's going to be aqueous. And this is balanced. My mole ratio is 1 to 1, or I should say 1 to 1. So that means that this many moles of HI also equals this many moles of NaOH. So now I know my moles of NaOH. I know my volume of NaOH from the problem. Let's find molarity. Molarity equals 0.0338 moles of NaOH divided by 35 milliliters, so 0.035 liters of NaOH. Do the math. 0.966 molar. Okay. Let me check something. My answer key doesn't match what I did here. Looks like I see a problem on my answer key. If you're following along, I accidentally wrote 0.0338 as 0.0388. So this is right, answer key is wrong. 68. Consider the following acid-base reaction. HSO3 minus plus sulfide ion yields sulfite ion plus HS minus. Right? Yep. So what's a bronzolary acid, bronzolary base, conjugate, acid and base? Alright, well, the bronzolary acid is the thing that donates the proton, or donates the H+. So let's see what loses the H+. Well, this obviously does because it goes from this to this. So this is my Bronsted-Lowry acid. This makes this my Bronsted-Lowry base because this must be receiving that proton. You can tell that it does because it goes from S2 minus to HS minus. Well, the acid turns into the conjugate base, so that's this. My base turns into my conjugate acid, just like that. Number 69. How many sig figs are in 51,100? 3 sig figs. 2.00, 3 sig figs. 0.00230, 3 sig figs. 500 point, 3 sig figs. 10,000.0, 6 sig figs. Those all count. And the last one, 0.0021, 2 sig figs. 70. Percent error equals actual minus experimental over actual, but that's an absolute value, times 100%. Now sometimes we use the terms actual or theoretical here. Basically, it's how far off you were. This is what you recorded in lab. It's how far off you were from what it should have been. So this is sometimes called theoretical, divided by what it should have been, which is theoretical. And because that's absolute value, if you get a negative, just make it positive. Percent yield is 71. And that is your actual yield. Well, again, I don't like the word actual. Let's call it experimental yield. So it's how much you actually got during lab divided by theoretical yield. So it's what you actually got divided by what you could have gotten in the perfect world times 100%. Number 72. If you expected to produce 36.2 grams of CO2 but actually produced 21.1 grams, percent error. So it's what you got minus what you should have gotten in absolute value. So it's 21.1 grams minus 36.2 grams divided by what you should have gotten, 36.2 in absolute value, times 100%. So this is going to be negative, but we'll just make it positive because it's absolute value. 36.2 divided by 36.2, which gives me 41.4%. My percent yield is what you actually got, 21.2 grams, divided by what you should have gotten, 36.2 grams, times 100%, which is 21.2 divided by 36.2, 58.6. And as you could probably notice, they equal 100. It's kind of the reverse way of measuring your error. looks like that was 73. No, that was 72. Okay, 73. How many moles of KOH are present in 250 grams? Nice and easy. 250 grams of KOH times 1 mole over, let's add it up. K is 39.0983 plus oxygen, which is 16, plus hydrogen, which is 1.008, equals 56.12 grams. Gram cancels gram. We get 4.46 moles. 74. Last page. How many total ions are present in the sample above? Alright. So this was a tricky problem. I didn't really like the wording of my problem here. So I have 4.46 moles of KOH. Well, KOH is an ionic formula unit, really. It's not a molecule. That consists of K plus and OH minus. So basically, for every one of these, I have 2 total moles. One of this and one of this. So what I want to do is multiply this by 2 total ions per mole of KOH. Actually, mole isn't even the right word there. It should be this. What I need to do is turn moles into formula units first. Okay? Because really that's not true what I just wrote. So let's turn this into how many formula units I have, or if this were an atom, it'd be how many atoms. So we're going to say 4.46 moles of KOH times Avogadro's number 6.626. No, thinking Planck's constant. 6.022 times 10 to the 26th. I'll say KOH units per mole of KOH. Moles of KOH cancel. So now this is how many KOH units I have, or formula units. Well, it's going to be 2 ions per KOH, because each KOH splits into K plus and OH minus. So let's do the math. 4.46 times 6.022 times 10 to the 20. Again, I'm mixing up my units here. That should be a 3. 10 to the 23rd times 2 gives me 5.37 times 10 to the 24th total ions. Let's check if I got that one on my answer key. Yep, slightly off. I said 5.36, so I must have rounded off. Anyway, let's go to 75. How many total atoms are present? Well, let's revert back to this. So let's change this up. So 75. Well, how many atoms of KOH do we have? I actually wish I hadn't erased that. Well, I have 1, 2, 3 atoms per. So let's do it this way. We need to turn moles into formula units again. So it's going to be times 6.022 times 10 to the 23rd. And that's going to get us into formula units. And then each formula unit gives me 3 atoms per unit. KOH. So it's going to be 4.46 times 6.022 times 10 to the 23rd times 3. 8.06 times 10 to the 24th atoms. See if that matches. Yes, it does. All right. 76. 76 says the Lewis structure for oxygen gas molecule. Well, I know oxygen gas is O2. So to draw this Lewis structure, I'm going to first count my electrons. 6 times 6, or 6 plus 6 gives me 12 total electrons. Now I'm going to draw my skeleton, OO. I'm going to add all my lone pairs to complete the octet rule. Okay. And now I'm going to count, see if it matches. 2, 4, 6, 8, 10, 12, 14. 14 is too many. So what I do is I erase a pair from each, create that double bond, and this is now complete. And technically, these electrons should be kind of cornered on the side of the oxygen, so it should be like this. Oxygen gas. Okay, 77. What is the pH of solutions with the following concentrations? Alright, well that first one is just going to be 5, because you just say negative log of 10 to the negative fifth. The second one, it's going to be negative log of 0.0000345, which gives me 4.46. And for that third one, well, we know OH minus, so let's find POH first, and then turn that into pH. So POH is negative log of the OH minus, so negative log of 0.0552 gives me 1.26, and that's my POH. Well, pH is 14 minus this, so it's just 12.74. And you might think I had too many sig figs here. Well, really, when you subtract, you're gonna include the number of decimal units here. So that's my pH, the third one. 78. 78, give the correct chemical names for the following. Well, that first one is going to be tin 4 oxide. The second one is copper 1 chloride, and the third one is magnesium nitrate. 79. Give the number of protons and electrons for the following. Well, calcium is going to have 20 protons, 20 electrons. Na plus is going to have 11 protons and only 10 electrons because it gave one away to form that plus. H plus has 1 proton and 0 electrons. And S2 minus has 16 protons and 18 electrons. Okay. Number 80 says the total number of protons and neutrons in the following. So Ca with that 41 means we have 20 protons and 21 neutrons, which, by the way, you always know the protons, it's the atomic number. 12 carbon means it has 6 protons and 6 neutrons. And barium-138, well, barium always has 56, so let's subtract 138 minus 56. Gives me 82 electrons. So 56 protons, 82 electrons. Number 81. How many grams of N2 are required to react with 100 grams of N2 according to the following reaction? Okay, so let's see what kind of problem we have here. It's just a regular stoichiometry problem. N2 plus 3H2 yields 2NH3. So my mole ratio is 1 to 3 to 2. So if I have 100 grams of H2 gas, we need to say 100 grams of H2 times my molar mass of H2, which is going to be 2.016. Well, it should be 1 mole over that. So 100 divided by 2.016 gives me 49.6 moles of H2. So the question says how many let me find it here. How many grams of N2 are required? Well, it's a 3 to 1 ratio here. So 3 to 1 means we're going to divide this by 3, which gives me 16.5 moles of N2. 16.5 moles. Let's convert that to grams. So N2 is going to be 14.01 times 2, so 28.02 grams per mole. And the answer I get is 463 grams of N2. Number 82. What volume of NH3 gas at STP could be produced from 100 grams of hydrogen gas in the above example? Assume excess nitrogen gas is present. Alright, well, we can save most of this. So let's see. Get rid of that just for the sake of space. Okay. And this even we don't really need for this problem. But anyway, we already calculated that this is how many moles of H2 I have. So we're going the other way now. It's 3 to 2. So we're basically, I mean, you could do it with the X. Oops, drop my calculator. You do it with the X, or you could just divide it by 1.5. So this gives me 33.1 moles of NH3. Let's see, do I ask for grams here? Oh no, I asked for volume. Alright, well if it's at STP, 33.1 moles of any gas times 22.4 liters per mole equals, with 3 sig figs, 741 liters. See if that matches what I said. I'm on 81. Or technically I'm on 82, and yep. Alright, so I'm on to 83 now. 83. How many moles of NH3 could be produced if 120 grams of nitrogen gas react with 21 grams of hydrogen gas? Alright, so this one will be a limiting reactant problem, it looks like. Yeah, we could probably eyeball it too. So I have N2 plus 3H2 yields 2NH3. We're given grams of each, so we need to convert both to moles. So 120 grams of H2 divided by 2.016 gives me 59.5 moles. And for my nitrogen, I have, oh, I did that wrong. That was my nitrogen. So 120 grams of nitrogen divided by 28.02 gives me 4.28 moles. For my hydrogen, let's see, I have 21 grams of hydrogen. So it's 21 divided by 2.016 gives me 10.4 with my proper sig figs. And yes, I can in fact eyeball this one. Basically, I need a 1 to 3 ratio. So if I have 4.28 moles, I would need 3 times that. Well, I could just tell this is, more than 4. So I would need at least 12, probably more like it's going to be 12.84, something like that. And I only have 10.4, so clearly this one is my limiting reactant, LR. Okay, so we're going to base what we get here off of our limiting reactant. Well, it's 3 to 2, so we're going to divide this by 1.5, which gives me 10.4 divided by 1.5 gives me 6.93 moles. By the way, if you couldn't really eyeball it like that, let's just make sure here. So assuming you didn't know, this would basically be a 1 to 2 ratio, so you would double this, and you would say 4.28 times 2, which would give you 8.56 mole. So basically, if you had this much N2 and all the hydrogen you needed, you would produce this much. If you had this much H2 and all the nitrogen you needed, you would produce this much. Whichever one gives you less, that's what you use as your limiting reactant. And whichever one gives you less is the true answer in this case. 84. Atomic mass of silicon, considering the following isotopes. Basically, you take the mass, multiply it by the percent abundance turned into a decimal. So 27.9769 times 0.9223. Store that in the calculator. Plus 28.9765 times 0.04 670 plus 29.9738 times 0.0310 gives me 28.09. Seem about right? Yeah, seems about right. Let's check my other answer. Yep, that's what I got. The unit there, by the way, was AMU, or you could also say grams per mole. Number 85, frequency of a wave. All right. So the formula we use for this, C equals lambda nu. We are looking for frequency, which is this. Frequency equals C over lambda, which equals 3.00 times 10 to the 8th meters per second, divided by my frequency. Divided by my wavelength, which is 9.23 times 10 to the negative 4th meters. Notice my unit, meter cancels meter, and this is why it's important to convert to meters. If I put centimeters down here, or nanometers, it wouldn't cancel. So 3 times 10 to the 8th divided by 9.23 times 10 to the negative 4th. Make sure your parentheses are correct here. The answer I get is 3.25 times 10 to the 11th. And my unit here is S to the minus 1, which is like per second or hertz, Hz. 86. What is the wavelength of a radio wave with a frequency of 8450 hertz? Okay, same formula, C equals lambda nu, except this time I'm solving for wavelength, so equals C over nu equals 3.00 times 10 to the 8th meters per second divided by, where is it? 8450 hertz. And for hertz, I like to do per second because it's that many peaks per second. You can see here that per second cancels per second. I'm left with just meters. So 3 times 10 to the 8th divided by 8450 gives me, and let's check sig figs here. 3 sig figs gives me 35,500 meters. So that's a gigantic wavelength, but some radio or TV waves can reach that large. Number 87. What's the energy of a wave with a frequency of 2.31 times 10 to the 15th hertz? New formula, energy equals Planck's constant times frequency. Well, in this case I'm solving for energy, so Planck's constant is 6.626 times 10 to the negative 34th joules times seconds, multiplying by my frequency, which is 2.31 to the 15th. And for my unit here, I like to write per second, because that's hertz. Now I could really easily see here that second cancels per second very nicely. I'm left with just joules. Let's see what we get. 6.626 times 10 to the negative 34th times parentheses 2.31 times 10 to the 15th, close parentheses, gives me 1.53 times 10 to the negative 18th, and my unit is joules. Double check my answer here. Yep. And the last one, 88. What's the energy of a wave with a wavelength of that many meters? Okay, so this is going to be a two-step problem. Well, the formula I need for energy, E equals Planck's constant times frequency. Well, I'm not given frequency. I'm given wavelength. So our other formula we're going to use is C equals lambda nu. That should be lambda nu, same thing. So basically I'm going to plug in my value for wavelength. I know C, so I'm going to get this value for nu. Plug that value in here. I know H, so that gives me E. Alright, so first we're going to solve this for frequency. So frequency equals C over lambda, which equals 3.00 times 10 to the 8th meters per second, divided by my wavelength. And I have 9.21 to the 10 to the negative 6th. You can see here, meter cancels meter. The unit we're going to be left with is per second, which is frequency. 3E8 divided by 9.21 e negative 6, that's in parentheses of course, 3.26 times 10 to the 13th hertz, or I'm just going to write per second because we'll notice that cancel. So anyway, that's my frequency, which I'm now going to plug into my formula here. So energy equals 3.26 times 10 to the 13th per second times 6.626 times 10 to the negative 34th joules times second. We can see here that per second cancels with seconds. I'm left with just joules. Let's get our last answer of the last problem and be done. 6.626 times 10 to the negative 34th, close parentheses, 2.16 times 10 to the negative 20th joules. That matches what I got. That's our answer. All right, study hard for the final.